So we're getting into chapter 9, and we're in chapter 9 we're going to do two things. We're going to extend our knowledge a little bit of what we did from the normal curve. And in particular, we're going to link in sampling and confidence that our sample actually represents the population. We're gonna find out a few things. It's gonna get a little bit messy at the beginning, but hopefully I can draw your attention to two things that we use, and they're kind of related together to give us confidence that our sample actually represents the population. Let's go back, because remember, at the beginning of the course, we were describing what statistics do, and one of them is that they make inferences. We see we take evidence from a sample or measurements from a sample, and we refer to the population. But how do we know that, right? Because we talked about sample size. I mean, a sample size of 5. How can that represent a population? Well, in actuality, it's not going to be that powerful. And we saw also that the larger the sample size we have, that more closely represents the population. If you go back and remember those blood pressure histograms, right? But you can't, sometimes it's not possible to get a sample size of, 3,000 or a sample size even of, 1,000. Sometimes you've got to work with sample sizes, if you're lucky, in the hundreds, and even less, right? What if it's a sample size of 40? So when you're working with smaller sample sizes, we know that we're kind of departing, we're moving further away from the population size, and so we kind of get a little bit confused. How can we depend upon our sample to represent the population, right? Because we want to be confident that we're making a correct inference. So there's two things that we can use, and they're linked together. One is the standard error of the mean. In essence, what that is we're going to estimate the population variance. But we're going to do it in a way to show you how the standard error can be used to give us a little bit of confidence about our sample means. And the second thing, which uses the standard error of the mean, is what we call a confidence interval. And when we take a look at a confidence interval, and you'll see confidence intervals a lot in the research literature. You will see confidence intervals. When we take a look at a confidence interval, that gives us again a bit of a okay, yeah, we're actually pretty confident that the sample represents the population. Now the problem with confidence intervals, as we're going to see, is we got to flip it around, just like we do in stats all the time, right? Before we said stats don't prove things, they disprove things. When we get to confidence intervals, we're going to say the opposite. We want to flip that around and say, how confident are we that the population mean falls closer to the sample mean? Okay, and I'll unpack that for you. So get ready for another flip coming up. So the learning goals for this section are going to be, well, obviously understand the concept of the standard error of the mean. And we're going to work with the confidence interval. Again, both of these are mechanisms that increase confidence that the sample represents the population. And then we'll do a little bit of calculation as well. Not only calculation, but also interpretation. The calculation part is easy. That, it's this, again, these are fractions, again, is what they are. And they're actually, one's a fraction, one's not. One's simply a product. It's the interpretation of the confidence interval can get a little bit tricky. That's going to be the trickier one. Standard error interpretation of what that value is pretty straightforward, but the confidence interval interpretation can get a little bit tricky. But we'll get through it. So this here is the real question, isn't it? How reliable is our sample mean? Because we want our sample to represent the population. And so, I mean, a bit of a thought experiment here. When we do sampling, or when researchers do sampling, sampling is hard work. It's hard to go and get people into studies, and sometimes it's really hard to get people into studies. Sometimes it takes years before you get a sample size that is adequate. And so there's some of the realities that go along with this. But what if we had, say, a population of 10,000 people, and I reach in and I draw out a random sample of 50 people, I measure them on a variable, and I get the mean and the standard deviation. And then I take those 50 people, I put them back into that population of 10,000, reach in again, take another sample of 50 individuals, bring them out, measure them on the same variable. Do you think those two sample means that I've just pulled, right, from the same population randomly,
Do you think those two same population means and standard deviations are going to be identical? Well, probably not. Will they be similar? Hopefully so, and likely so. And what if I were to take those 50 people and throw them back in again to the population of 10,000, reach in again, draw another random sample of 50 people and measure that sample mean? I mean, we could do this on and on and on and on and on. The hope is that we would see that the sample means and standard deviations would be pretty similar every time we do this. But there's always the chance, right, that you reach into that sample, that population, pull out that sample of 50, and that might be the 60th mean that you've done this, and all of a sudden, whoa, you have a sample mean and a standard deviation that is unlike anything you've done before. It might be really, really small, or it might be really, really large compared to the original 59 sample means. Okay? And so you kind of get to the place where, well, how can we be sure what really is the truth? And this is the quandary that researchers find themselves in. So what researchers can do is, instead of doing sample after sample after sample and try and find, like a grand average mean or something, they can take one sample and they can look at the standard error and confidence intervals to give them a sense of, yeah, we're on the right track here with respect to our sample mean being similar to the population mean. Okay, I've showed you this slide before where we have our visual example, again, of samples representing populations, hopefully. And again, even in this example here, what we have is we have our sample mean is kind of close to the population parameter here, right? This is our sample statistic. This is coming up in the PowerPoint slides, I think, where I talk about point estimates, right? This is a point estimate of some sort of population parameter, right? We call the population mean a parameter, and we call our sample mean, we call it a statistic. And so the statistic is supposed to be close to the parameter. In this case here, it looks pretty close. But again, we also have the aspect of variance with both the population parameter and also with the sample statistic parameter, sample statistic. We also have to consider the variance. And so are the means the same, and also are the variances the same? Right? We make that assumption, but again, we can see here we're always going to be a little bit off. Okay, we're always going to be a little bit off. So when we draw a sample again from our population, we want to know how close we are to the actual population mean or parameter, I think this closeness. So we don't really know. We kind of assume. I mean, a lot of times it's the way we do the sampling, okay? And you'll cover that when you take a research methodology course. You get into sampling theory and sampling ways of sampling. And let's say we do everything right, okay? We actually have the opportunity to do a random sample. But is there something more that we could do to give us greater confidence? And there's two things that we can do. And these two things are, number one, we're going to calculate and interpret the standard error of the measurement. And the second thing we're going to do is we're going to calculate and interpret what we call a confidence interval. Sometimes you'll see this expressed as confidence limits in the literature. Again, I'm sorry, sometimes there's different nomenclature for describing the same thing. Okay, and they're fairly easy to calculate. These are not hard calculations. You can do some hand cranked ones, right, with some practice assignments. It's the interpretation that gets a little bit tricky. So let's do the first one here. We'll ease ourselves into that. And this again is the standard error of the mean. So y'all are a little bit lucky in the sense that when I teach this section to my class face to face, at least how I've done that in the past, I kind of take a bit of a long cut to get to the standard error of the mean, and I decided not to do that this time around, mostly because I think it would make things confusing. So I'm trying to pick the pathway of least resistance. I can cover it for you a little bit near the end if you like. If you're really curious about this, hit me up and I can tell you more about it. But I'm just going to cut to the chase and get to this here so we can anchor ourselves and move on. We know what the standard deviation is about a sample mean, right? That expresses the variance of the sample. So if the standard deviation describes the variance of a sample, right, then
what if we were to try and find out or estimate what the standard deviation was of the population? And that's what the standard error of the mean is. It estimates the population variance. That's what it does. And there's going to be different sizes of standard errors, as we're going to see. And the standard error is going to depend upon two things in terms of calculating it. Number one, it's going to depend upon the standard deviation of our sample, and it's also going to depend upon the sample size. Now that kind of makes a little bit of sense. At least the sample size makes a bit of sense, doesn't it, right? Because we know that the larger our sample size is, the closer it gets to the population. So now we begin to have these worlds colliding here, where we're talking about variance and now sample size, and how do these two things together influence or help us estimate the population variance? So we need to draw our attention back to the normal curve here for a second. And I want you to notice a couple things that are similar about the normal curve, and one thing that's actually different. Notice that with the normal curve, right, we see the same proportionality, which makes sense because we're trying to actually estimate a population now, right? And so the normal curve really applies. But notice on the bottom, instead of having z-scores or standard deviations, now we have units of standard error. Okay, and so if this was a sample and these were standard deviations or z-scores, the proportion would stay the same. The normal curve stays the same. Because it's a population, same thing applies. Now we're dealing with standard errors now and not standard deviations or z-scores. But the proportionality still stays the same. And the mean still stays the same. Okay, you got your population mean in the center, and now we talk about how many standard errors a score can be from the population. So we're just changing the nomenclature just a little bit, but it means the same thing in terms of the normal curve itself and also the proportions within the normal curve. And here comes that question again. So what? Why is this important? It's important when we get to t-tests. So I'll bring you back to this normal curve and standard errors, right? When we get to t-tests, I'll explain that a little bit further. That's why I kind of just pause here, just take a look. Now, just remember, because we're dealing with a normal curve and population, we've now switched out the standard deviations. We've now inputted the standard errors because the standard error is the population variance. So here's what the standard error can do for us. We know we don't want our sample mean to fall too far from the population mean, right? We're taking a chance on that when we do our sampling. Here's what, and this is the thing in the center here, okay? And I think it only happens once, so let's pay attention to it. The standard error lets us know how our sample mean is likely to deviate from the population mean. Okay, it's a bit of an indicator. It's one of two indicators. It's probably the least sensitive. The confidence interval gives us a little bit more sensitivity, but it gives us some sort of guideline here. In essence, and I've highlighted this in yellow, the smaller the standard error, the closer the sample mean is to the population mean. Okay, the smaller the standard error, the closer the sample mean is to the population mean. This is probably about as clear as I can make it. I'm probably butchering it in some way. Some statistician will come along and say, well, you're missing a few important nerdy points here. But for us and our basic scaffolding of knowledge of statistics, so we don't get lost, we don't get bucked off the hayride here, the standard error lets us know how likely the sample mean is to deviate from the population mean. And the smaller the standard error is, the closer our sample mean is to the population mean. Here's the math side of things, and it's actually not that bad. It's just simply another fraction. So on the left-hand side here, we have our standard error, and to calculate our standard error, it's pretty simple. We take our standard deviation that we have here from our sample and divide it by the square root of the sample size. Now, we're going to notice the standard error is going to be affected by the size of either of these, right? So if I've got a larger standard deviation, for example, that's going to push the standard error up. If I've got a larger sample size, it's going to push the standard error down. And so this is where now we begin to have this interaction between our sample size and our variance to give us some indication of the reliability of our sample. So Two things. Let's consider a couple of things. What happens to the standard error if the standard deviation is large or if it's small? And how does the sample size affect the standard error? Let's look at a couple of examples coming up. So the math here is pretty straightforward, right? And I've got some examples coming up after this slide here. But we see, we'll look at how standard deviation and how the sample size affect the standard error. So if the standard deviation increases, we know that there's going to be an increase in the standard error. How do we know that? Well, we go back to our old mathy math stuff, and we know that if this gets larger on the top, anytime the numerator gets larger on the top, assuming the denominator doesn't change in size, this means this is going to increase. And so what we're finding out now is that variability has implications for the standard error. If there's large variability, that is to say if there's a large standard deviation, then the standard error is going to go up. On the flip side, if the standard deviation decreases, right, where variability is less, more scores clustered close to the mean, then this is going to decrease the standard error. And so it gets a bit more complicated, and I'll bring in how both these two things tie together after we go through a few examples here. Okay, so here's a tale of two standard deviations. And again, this is just to kind of show you, again, simple math. I know you might be going, Mike, this math is way too simple. People have math phobia. So I'm going to go really simple with this here. So here's our first example. I got a sample size of 100, okay? And the first example here, I've got a standard deviation of 20, and I want to calculate what the standard error of the mean is, right, or the population variance. That's pretty simple, right? I take the standard deviation, which is 20, right, divide that by the square root of the sample size. Let's not forget about the square root thing, right? So the square root of 100 is 10, right? I use 100 to make things easier for me in terms of doing math really quickly. And so 20 divided by 10 is going to give me a standard error of 2. Right? If I had another sample, right, but this time the standard deviation is 40, when I calculate the standard error of the mean using the same way, I get a standard error of 4, which means the population variance is larger. So again, this is a population variance estimate. We don't know for sure because we don't know what the population is, right? So this is where it gets a bit funny. But nevertheless, if we're comparing two standard errors here, we would have greater confidence that the sample was closer to the population mean if I had a smaller standard error. In this case here, this sample here would be a better estimate of the population because the standard error is less than the second example down here. So what does this mean for the researcher? Okay, this means that if there's more variability in the sample, the standard error is going to increase. Okay, that's fine. That's fine. Is there a way we can actually modulate the standard error? Like if this gets really large, is there a way to kind of maybe bring this down a little bit? And there is. If I know that the variability in my sample is going to be large, let's say that I wanted to measure the variable age, and my population was going to be anyone from children all the way up to people in their 80s, okay? I know off the top, because I know there's going to be kids and children and teenagers and young adults and middle-aged people and people in their 80s in the sample, I'm going to have a large amount of variability in the age itself, right? We just know that. You don't even need to do a standard deviation on it. You know you've got a lot of different ages in there, right? Small to high. So if I want to get a better sense of what the population is, and I know my standard deviation of the variability is going to be high, I've got to compensate by increasing my sample size. Okay? Because if I have a larger sample size, even though the standard deviation is going to be large, if I've got a larger sample size, that's actually going to bring my standard error down a little bit. So sometimes we can actually know things ahead of time. If I know ahead of time, yeah, if I know my field and I know my population, well, then that's going to have implications for the sample size. There's actually a way to calculate how many people you need in a sample. I'm not sure I'll get a chance to do it in our session. We might run out of time, but I'll try and fit it in. It's complicated, but I'll try and do that. So just kind of going back to some of the application side of things here. We want our sample to represent the population as best as we can. If the standard deviation is quite large in my sample, again, sometimes I know this ahead of time, right? Again, know your field. I can actually bring the standard error down a little bit if I actually increase my sample size. And so let's look at the second one here. The second one here is what if we What if we fool around a bit with our sample size? What's going to happen to the standard error? Well, we know if the sample size is small, this will cause an increase in the standard error. Remember, we're taking the square root of something. So if my sample size was 4 on the bottom, the square root of 4 is going to be 2. So when I divide 2 into something up here, that's going to dramatically increase my standard error. And the funny thing about this too is a lot of times with small sample sizes, I'm going to have a large standard deviation anyway. Okay, that can happen. So this is why we want a sample size of sufficient magnitude, because the larger the sample size that we have, right, that's going to have a less dramatic effect on increasing the standard error. Okay. Now, conversely, if the sample size is really large, then the standard error is going to decrease, right? What if I was measuring age again, and I had a sample size of 100,000, right, or 1,000,000? Okay, well, the square root of 1,000,000 is 1,000. My standard error, my standard deviation could be really small for age. It might be 30 years, but 30 years divided by 1,000, well, your standard error is going to be really, really small. So what that tells us is your sample size, right? If I've got 1,000,000 people, you've got a pretty close approximation to what the population parameter really is. So we do this. This is why we focus on sample size. This is why sample size, it's not everything, but it becomes a big deal when you're doing research. Why? Because I want my sample to represent the population. If I've got a large sample size, that's going to bring my standard error down. And we know from before, the smaller the standard error, the greater the likelihood my sample actually is, my sample statistic is pretty close to the population parameter. And that's what we want. And again, a couple of mathy things here. So here's our second example, and all I've done this time is I've actually kept the standard deviation the same, and all I've done is simply manipulate the sample size. So given a sample size of 100 and a standard deviation of 20, what's the standard error of the mean? Well, I do the math and I get a value of 2. But what if I increased the sample size by a factor of 10 and kept the standard deviation the same? Again, same population. You're not going to expect the standard deviation to change that much. It might change a little bit, but in this case, we've kept it constant. When I do the math here, I get a standard error of the mean of 0.63. Well, 0.63 is much like it's one third the size of 2. So this goes down by a factor of 3. And so in this case here, my sample size of 100, that whatever the sample statistic I'm measuring, it's going to be much closer to the population statistic than it would be if I had a sample size of 100. And again, so what does this mean? With the larger sample size, we have less error. If we have less error, we can estimate more precisely the parameters of the population. Now, one of the things that I didn't talk about is what if my population is really, really specific? Okay, let's say, for example, I was measuring, well-trained endurance runners. Now, well-trained endurance runners have very similar characteristics, okay? They've got very high aerobic capacities. They've got very low percentage of body fat, as an example. They've got very low resting heart rates. There's not a lot of variability in that sample of in that particular population, okay? So what that means then sometimes is that if I know my population doesn't have a lot of variance in it, by the way I describe what my population is, so in this case here, highly trained endurance runners, right? Then that means I don't need to have a large sample size, right? When you think back to that equation, I don't have it here for you on the slide, I'm sorry, but think back to the equation of standard error. It's the standard deviation divided by the square root of the sample size. Well, look, if my standard deviation is going to be small because there's not a lot of variability in my sample, what that means is I don't have to have as large a sample size to do it, right? If your standard deviation is really small, my sample size doesn't have to be big either if I want a reasonable standard error. And so a lot of times, this is what researchers know going into it. If they have very, very precise, if there's not a lot of variability in the population that they're measuring, they know that their sample size doesn't have to be that large, okay? And that's great. There's some limitations to the research findings because your research findings are only going to be applicable to that one particular group, well-trained endurance runners. You couldn't take the data there and infer it onto the general population. So there's going to be limitations to what you can infer, right, depending upon your population. So it gets a bit complicated. But again, there again is just another example where you can have, in some cases, okay, I don't have a lot of variability in my sample, right? In this, because of the population that I'm measuring, and that also means I don't have to have as large a sample size. So this slide here kind of pulls things together. And what we've been discussing here is this relationship between variance and the sample size as it relates to confidence that my sample represents the population. And we've used two things that we know already, and one thing that we introduced, right? We knew what the sample standard deviation is, we know what sample size is, and together, mathematically, we can work out what the standard error is. And we know that a small standard error means the sample size likely represents the population parameter fairly closely. Larger standard error, there's less reliability that it is. And there's that actually that has some implications later on for statistical significance, believe it or not. And so ideally we want to have a small standard error. What if we don't? What if we have a large standard error? That's okay too. You can still do statistics with large standard errors, as we're going to get into when we get into t-tests. It just gets a bit harder to show to show what we call significant associations and significant differences, and I'll explain that a little bit later on. It doesn't mean just because you have a large standard error doesn't mean you can't run any statistics. You can. It just gets a lot tougher to show that there really was a true difference between two means, and again, I'll explain that a little bit later.
We've seen that the standard error has some utility here then, right? At least with respect to understanding how far apart or how close the sample mean is from the population mean. It gives some indication. It's not perfect, right? And the other thing too is you kind of have to know something about the variable that you're measuring. It gives us some utility, of course, but is there something else that might give us a bit more confidence in our sample? And that's the question. Standard error is somewhat helpful. Is there something else that has a little bit more of a, it's more intuitive, so to speak. And what we're going to cover next is that, and it's called the confidence interval. And we'll see that with the confidence interval, we actually kind of have to interpret things backwards a little bit. I'm sorry, that's just how things go. A bit of a heads up to the slide that's coming up next. It kind of sets the stage or paints the picture of how confidence intervals operate. And it's a little bit of an unsettling slide to a certain extent, because it really shows us how uncertainty plays a role in statistics. Uncertainty is always going to be there. Again, this is why we can never prove things with statistics, and you'll see part of that on the next slide as it sets things up for us to understand confidence intervals.
So before we get into confidence intervals, just a bit of a reminder. Remember that the population parameter, the stuff that we're really interested in, and the population standard deviation is almost always not known. Okay, it's not known. And so, and think about what we've been doing here so far. We've been saying, I want my sample to represent closely as possible the population, but the thing is, we don't know what the population value is. And so we have a bit of a quandary here. Take a look at this, right? So we have samples. We use samples to infer to populations, but the sample is an estimate of the population itself. But the population parameter, the very thing we're trying to estimate, that's also not known. So we're using an estimate to estimate an unknown quantity. That's kind of bizarre, right? Here I have that here on this third point here. So we're using an estimate, the sample statistic, to estimate the population parameter, which is unknown. And then on top of that, we want our sample statistics, the mean of the standard deviation, to be similar to the population parameters. So it's like, it's worse than Jell-O, trying to nail Jell-O to a wall. What do we do with this quandary, right? I just like to pause here sometimes and take a look at this and really take a step back and see what we're working with. And it almost seems like an impossibility, right? Let's take a bullet and let's hit another bullet that's coming at us from 5 miles away and see if we can do it. It's about the same level of challenge. And again, just to kind of reiterate, why I believe that with statistics, very often we take these small leaps of faith, don't we? Right? Because we're uncertain. And this slide here kind of shows us the level of uncertainty. But you know what the really weird thing is? The really weird thing is, despite all of this here, if you do an experiment correctly, if you follow the procedures, if you use reliable, valid measures, all those things, when you run your statistics, you can do some amazing things and have some fantastic results that you can infer and make predictions into the future with phenomenal accuracy. It's quite amazing. So this looks a bit daunting, and you know, how are we going to do this? And I'm afraid the answer is going to be okay. It's not going to be a fantastic answer. It's going to be an okay answer. But we can still do this. We can still do this. Let's see how we can use confidence intervals. Okay, so here we go. Now we know it's unreasonable to expect that the mean we obtain from a single sample is going to be identical to the unknown population mean, right? And we can accept that. It doesn't have to be perfect. We'd like it to be close, right? Doesn't have to be perfect. So if we're estimating a population mean, which we don't know, we need to state, along with our sample mean, some measure of our confidence. Now, we started with the standard error, and we can use that for a bit, but we can go a little bit further, right? So what we do is we develop what are called confidence intervals. Because we're not sure about the population mean itself, maybe what we have is some sort of larger fuzzy dot where our sample might fit into, if you want to think about it that way. Okay, so it's not dot on dot or bullet on bullet. Maybe it's bullet flying into a big thing of jello or something, right? Because we're not sure what the bullet would be our sample statistic, and the big bowl of jello would be our population, what we think is the population mean, because it could have a range to it, right? But to understand confidence intervals, we need to think of them a little bit in reverse. Instead of asking the question, hey, how close is our sample mean to the population mean? We have to think about it reverse. We look at it this way: how confident can we be that the population mean falls close to our sample mean? Okay, how confident can we be that the population mean falls close to our sample mean? I want you to begin to think that way. I know I've been doing everything else the other way. How close is our sample mean to the population mean? And I did that on purpose because we can kind of get our hands on the sample mean, right? We can get in there and we can wrestle with it and measure it and do all those things. And so it makes sense. Okay, here's my sample mean, and we're going to go from my sample mean and infer to the population, right? So I start from the sample mean, but I want you to think in reverse now, and I want you to think, how close did the population mean fall to our sample mean? Now, at first glance, that just might appear to be semantics, right? Aren't you saying the same thing? Kind of, but not really. Remember, the only thing we can actually measure is the sample statistic. Look, I can walk in, right? If you were my class, I could walk in there and measure everybody's height. And I've got a hard measurement for it, right? Especially if it's reliable and valid, I can depend upon that sample measurement. What I don't know is the population mean. I know what my sample measurement is. I know what my sample mean is. What I don't know is what the population mean is. So this is why we have to go, I've got in my hands my sample mean. How close does the population mean or population parameter fall to my sample mean? That's why we have to think about it that way. And it makes more sense once we unpack the confidence interval in terms of its mathematics too. So just to kind of extend from the previous slide, I'm going to introduce a term here that is sort of, it's mostly helpful for describing confidence intervals. When we estimate a population parameter, which is what we do, right, when we take a sample, that single number, whatever that sample mean is, we call that a point estimate. Okay, that's what I meant by the bullet. Okay, that's our point estimate. This is our bullet measure here. Okay, and so the sample mean is a point estimate. Right, the sample mean is a point estimate. The reason why I bring up point estimate is because the confidence interval is a calculation, And this calculation is a range or interval of values that surround the point estimate, right? So we use the sample mean actually and the standard error to calculate this range of values where we think the population parameter resides. That's what we do. So we start with our point estimate, which is our sample mean. We throw in the standard error, we throw in a couple of other things, and mathematically, and then we get this range of values where we think the population parameter, or the population mean, if you would, falls. And it's a range. It's not like our sample point estimate where I can actually go in and measure that and get kind of a hard concrete value. Because we're estimating the population mean, and because there's error associated with it, we like to talk about an interval or a probability of values wherein the population mean falls. Okay, that's what this means. This is why we have this confidence interval. We're going to use the sample point estimate along with the standard error, which we can now calculate, and create this interval range where we think the population parameter falls into.
And to extend from the previous slide, we have to put some qualifiers on this range, right, on this interval. And so when we say we expect the population mean to fall inside this interval, we can say, again, mathematically, we can express it in a couple of different ways. We can express it as saying it one way, 95% of the time, the population mean is going to fall within this particular range of values. Or we can, in some cases, say 99% of the time, we expect the population to fall within this range of values, within this interval range. Now, there's a bit of a caveat in terms of what that means. What this means is if I were to do repeated sampling. So here's an example. Let's say I set up a 95% confidence interval, and the next slide we'll get into the math. But I set up this interval, and let's say this interval is based upon a sample size of 100. So I reach into the population, I pull out a sample size of 100, and I can get a confidence interval, right, based upon that, based upon the sample mean and the standard error, which I can now calculate. And I set up a confidence interval. If I were to do this 100 times, take this value, the sample size of 100, throw them back into the population, take out another sample of 100. If I do that 100 times, 95 times out of those 100 times that I do that, the population mean will fall within that confidence interval that I create based upon that sample. 5% of the time they won't, but 95% of the time it will. So this is what we mean when we talk about a 95% or a 99% confidence interval. If it's a 99% confidence interval, then 99 times out of 100 of repeated sampling, same sample size from the same population, 99 times out of 100, the population mean is going to fall inside that particular confidence interval.
So to calculate a confidence interval, we have, well, here's our CI. So this is what we want to calculate. It's simply this range, right? So it's going to be, the math here is pretty straightforward. It's the observed statistic, that is to say this is our sample mean. Okay, that's our point estimate. I said before we use our point estimate to calculate this interval. Okay, so plus or minus. Now you need the plus or minus because it's an interval. That interval is going to be around the sample mean, so to speak, or we're creating this interval around the sample mean or using the sample mean. And it's going to be plus or minus, and in brackets, the standard error. Okay, we know the standard error is the standard deviation of our sample mean divided by the square root of the sample size, so we can do that, multiplied by the specific confidence level of value. It's either going to be 95% confidence level or 99% confidence level. Rarely will you see a 90% confidence level. You'll usually see 95 or 99%. I'm going to specify that a little bit more on the next slide as to what this means. So when we're working through that calculation, we don't multiply the standard error by 95%. We actually multiply it by plus or minus. We actually multiply it by 1.96 standard errors. I'll give an example on the next number of slides coming up. 99% confidence interval, we use the value 2.58, which is 2.58 standard errors. And so these are the values that are already set, and these are the values that we use. Now, note also that because we're assessing the probability that a population mean falls into a confidence interval, we use the standard errors and not the standard deviations in the equation, right? That kind of makes sense. Confidence interval has to do with where the population mean falls. Therefore, we have to use standard errors and not standard deviations. So the best way to do it is to show you an example. So let's say that I draw a sample size of 50 from a population, right? The mean is 40 and the standard deviation is 15. What I want to do is I want to calculate the 95% confidence interval for my sample. Okay, again, that's going to be a band of numbers, a lower number and a higher number, where I think 95 times out of 100, the population mean is going to fall. Okay, so we're going to do the calculation. That's the easy part. The harder part is the second part there, and it's explain what you have calculated. And I'm going to put this out for you in grand details. You can always go back to that slide and look especially at the explanation. So the first thing we need to do in our equation, if we're going to calculate a confidence interval, is we need to calculate the standard error of the mean, because that was part of the equation. And so to calculate the standard error of the mean, we know what to do. So from the previous data, the standard error of the mean in this case here is going to be the standard deviation divided by the square root of the sample size, which is 15 divided by the square root of 50, which gives us a value of 2.12. And so we plug then our values into the equation. So here we go. So the confidence interval is equal to the mean plus or minus 1.96, because it's a 95% confidence interval, multiplied by the standard error. And so here we have the value of 40, that was our mean, plus or minus 1.96 multiplied by 2.12, because that was the standard error that we calculated. This gives us a value of 40 plus or minus 4.15. Now, unlike, the mean and the standard deviation, this time we actually have to do the math here and finish it off. So to get the interval range, we've got to go first the lower end, 40 minus 4.15. That's going to give us 35.85. And then 40 plus 4.15, that's going to give us 44.15. And so the confidence interval is going to be this. The 95% confidence interval, based upon all the previous data, is going to be a range between 35.85 and 44.15. This is not a minus sign, this is a range sign. So 35.85 to 44.15, that's the interval, or that's the confidence interval that we have created. Now the question is, what does that mean? So let's explain what we've done here. We've created this interval, this range of values, right? We've got this lower range here, 35.85, and an upper range here, 44.15. And we've identified this as a 95% confidence interval. And what is this interval surrounding? Notice what it's surrounding. In the center here is the symbol mu, which stands for the population mean. So we have constructed a confidence interval wherein we are confident that the true population mean will fall within this interval 95 out of 100 times of repeated sampling using the same sample size. What that also means is 5 times out of those 100 times, the true population mean is going to fall outside that band. But 95% of the time, or 95% of the time, it's going to fall within that band. Those are pretty good odds. Those are pretty good odds. Now, the other thing that actually helps you understand, your chances of getting it right, that is to say that your population mean is close to the sample mean, is how far apart these values are around the population mean. So there's a difference of about maybe 8 units or so in between the lower value and the upper value. Okay, that's not too bad. If this upper value was, say, 101.6, right, it's way over here, that's a really, really wide confidence interval. I wouldn't be very confident that we came close, that the population mean was close to our sample mean. I wouldn't be confident with that. The tighter the range, that is to say, the less the difference in between the upper value and the lower value, the greater confidence we have that the population mean lies close to the sample mean.
This slide here is an extension of the previous slide, and I almost hesitate to show it to you, but it's kind of important to let you know how these confidence intervals work. So we know that when we set up a confidence interval, we're setting up a band wherein we think that the population mean is going to fall 95 times out of 100. What you need to know, and this kind of relates back to sample reliability, is that this confidence interval, right, is going to change every single time you sample. Right? Even if it's the same sample number that I pull out, a sample size of 50 out of the same population every single time, this confidence band is going to change a little bit. Why is that? Because every time I draw a sample, the mean is going to change a little bit, right? So in this first example here with the sample size of 50, the mean is 40, and that's going to give me this confidence interval here, 35.85 to 44.15, right? If I were to throw this 50 back into the population, take another sample of 50, randomly of course, this time the mean might be 42. And if the sampling error stays constant, even if with the sampling error staying constant, I'm still going to have a different confidence interval. But if you notice, these confidence bands here are still fairly close together, right? So a lot of times it depends upon what the mean is going to be. Anyway, I state this because this is what happens every time you put together a confidence interval. A lot of times students think, well, this is going to be the confidence interval and it's etched in stone. It's not. It's going to be different every single time we take a sample, even if it's the same sample size, randomly taken from the same population, you are going to have a different confidence interval. So it's always kind of weird to express it as, well, here's what my confidence interval means is 95% of the time, the same sample size that I use to calculate this, the population mean is going to fall within this range 95 times out of 100 times. So it's just a little bit more of an extended explanation of the confidence interval.
So we're at the end here, and let's just summarize what we've done today. Sometimes the summaries is a lot easier. It's easy to get lost in this rabbit hole of trying to figure out what is going on when we introduce a new concept. But here we go. We want our sample to reflect the population as closely as possible. Of course we do, because we're making inferences. And statistics, a lot of statistics is about inferences. We can use the standard error of the mean to show us, or to give us an indication how close the sample mean is to the population mean. The smaller the standard error, right, the closer our sample mean is to the population mean. So we take a look at that. And we also have to consider now that both the sample size and the standard deviation of the sample will influence the standard error. As a matter of fact, I said that if we know ahead of time that there's going to be a large amount of variability if we know there's a large amount of variability in our population, we can expect a large amount of variability in our sample. And so what that means is, in some cases, in some cases, a large standard deviation is going to inflate the standard error, and so we can compensate for that by having a larger sample size. That's going to mitigate the size of the standard error to a certain extent. The second thing we did was we could also take a look at confidence intervals to give us some confidence about our sample reflecting the population mean. And so we just went through this, and we said that, the confidence intervals are based on the standard error when calculated, and it tells us how likely the population mean will fall within a certain range, right? Either 95 or 99% of the time. And this certain range is what we calculate based upon our sample. And so it's kind of like putting the cart before the horse, right? We're really interested in the horse, and the horse generally pulls the cart. But the thing is, we don't know much about the horse. And so what we do is we work with the cart to create, or to give us an indication of what the horse is like. That's kind of what we're doing here. Anyway, taken together, both of these values, both of these formula, these concepts, standard error and confidence intervals, can be considered to give us a little bit of greater sense of stability or confidence that our sample reflects the population. In conclusion, when you read the literature, you will not see the standard error that much. Okay, now I spent all this time on the standard error, and now you're looking at me going, great, we do all this, and I'm not going to see it. No, you're not going to see it that much. I had a prof at UBC, and he just said, I don't know why. In his mind, he just said, journals should always report the standard error, not the standard deviation, because it gives us more information, and I tend to agree. But we need to understand the standard error before we get into t-tests, and I'll explain that in Chapter 11. The confidence interval you will see. You'll see the confidence interval an awful lot. My grad school friends in nursing, I know there's a few of you in here in the class, when you get to things like odds ratios and risk ratios, that's more of an advanced type of statistic in epidemiology. You will